These are the notes for AP Calculus on the topic of logistic growth. So, logistic growth differential equations are used to model the growth of something, often populations. It has an upper limit as time approaches infinity called C, which is also referred to as the carrying capacity. So what that's saying is the limit as time approaches infinity of the population function, I'll just call it P of T, is equal to the carrying capacity, C. So we'll see what that looks like graphically in just a minute. So you just want to be familiar with the general form of the logistic growth differential equation, because they all have to fit the same form. You have to recognize it, and once you do, then you can apply some general things to the graph of it. So it's given by dp dt equals, what's interesting about though is the derivative, notice, doesn't have t in it, even though it's a function of time here. It just has two constants, which we're calling k and c. And c is, again, is the carrying capacity. So to get it in this form, where both these are constants, the key is to be exactly in this form, as you can see, this factor form, so that you can see the carrying capacity right here. C is whatever that constant is. In order for that to be the carrying capacity, this p right here, which is the same variable as right here, oftentimes it's p, but it could be something else, that has to be isolated. If it's not, then that's what you have to do to get it into this form. Okay. So once it's in that form, let's take a look at what the graph looks like. It has this general shape to it here, where this axis is the population P of T, and this axis is the time T. So the limit as T approaches infinity, so as we head off to the right, is C. So you can see that on the graph. Notice that how it kind of levels off here. It's not perfectly level, but it's really close to it. That's where we actually have a horizontal asymptote on the graph. Oops. So on the graph, it looks like this. Oops, let me get my color here. So right there, that horizontal asymptote that this graph is getting closer and closer to there, that is the carrying capacity. In other words, the population, there's some upper limit for whatever reason. Could be environmental, could be the type of population it's representing. There's some upper limit that it cannot exceed. So it gets closer and closer to that over time, but it doesn't ever exceed it. If it models, again, not all populations grow logistically, but sometimes they do, if they fit this, if their derivative fits this form here. So then on the graph, let's look at some key features here. So this is at time 0, this point right here. This represents the initial population of whatever it is. This is what it starts at time 0. Okay. And of course it has to be something positive, but it can't be negative. You can't have a negative number of animals or something. Something positive, it can't be 0, otherwise there's nothing to grow. It has to be something positive. And then the shape of the graph, it has the general shape here, where it's increasing. You can see it looks like concave up until some point right here. You can see it switches to concave down. And that point is an important feature of the graph here. Okay? That always occurs where it switches from concave up shape like a cup, remember? So this part of the graph is concave up. And then right here it switches to concave down the rest of the way. And that, remember when it's a point that switches from concave up to concave down or vice versa, remember that's referred to as a point of inflection. So it is a point of inflection. Now we're used to on most graphs thinking about the x-coordinate, in this case the t-coordinate, where the point of inflection occurs. And that could be various times. They could differ depending on the problem. But what's always the same on these logistic growth problems is that point of inflection always occurs on this axis whenever the population is exactly 1/2 of the carrying capacity. Okay, so if the carrying capacity is 1,000, this will occur when the population is 500, half of it. Okay. And this point of inflection is also important because if we think about the slope, when it's concave up, the slope is increasing until right there, and then the slope starts decreasing. So sometimes you're asked about where the maximum slope is, or how it's often worded is when the population grows the fastest. So this point of inflection on these logistic growth problems is also when the population is growing the fastest. Because that's when the slope, which is the derivative, represents the rate of change of the population, is the greatest, okay? The greatest slope. So those are some key features that you're always going to see. You can see that right here. When a population is modeled using the logistic growth equation, the population always grows the fastest when it's half the carrying capacity. And it's because that occurs right at the point of inflection why that is true. So those are the general features of the graph here. Now let's take a look at some specific problems that will just grow logistically. Okay? So a population is modeled by a function p that satisfies. So sometimes they'll actually tell you it's logistic differential equation. So you know that it fits that. So it asks us all these questions, but they won't always. Sometimes they will put it in this form to start with. Those are the easiest ones. But sometimes you'll have to modify it a little bit yourself. And remember, this variable here, whatever it is, usually p, that has to be isolated to be in this general form for the logistic equation. Notice it's not here because it's p divided by 200. So the way we can get it to be in the correct form is by using factoring. Notice we've got a p over 5 out in front. And then what you can do to get this p isolated is factor out its coefficient is 1 over 200. So you can factor out the 1 over 200. And then what you're left with, the trickiest part is figuring out what's left of this 2. So remember, factoring something out is like dividing by it. So 2 divided by 1 over 200 is the same as 2 times the reciprocal 200 over 1. So that's going to be 400 is what's going to be left there. And you can double check if you're not sure. If you distribute it out this 1 over 200 times 400, so you get 400 over 200, which does in fact give you back 2. And then minus, now since we factored out the coefficient 1 over 200, all that's left is p. So now it's in the general form of a logistic growth differential equation, because that p is isolated like this. And now we can see our constant k and our constant c. You could simplify this out in front to be p over 1,000 if you want to. You don't have to, but you could. And then it's 5 times 200. And then you'd have 400 minus p here. So now it says if p of 0 is 30, what is the limit as t approaches infinity? So what we're going to do actually, before we answer these questions, is use this. Notice that's on all the problems here. And actually, and the form we now have it in, and sketch a graph of what this looks like. But using the graph will be easy to kind of see the answers to any potential question they could ask about these. So remember, it has the general shape like this. concave up, and concave down, approaching some horizontal asymptote like that. And the P of 0 equals 30. Remember, this is T. This is P of T right here, the y-axis. And this is that's the population, and this is time. Well, that 30, that's giving you the initial population right there. So. And then the carrying capacity, remember in the general form, is this constant C right here. Once P is isolated, this constant, whatever it is, tells you the carrying capacity. In this case, you can see it's 400. That's what's going to go right there. And then you can draw a horizontal asymptote there again. Oops. So at 400, that's the carrying capacity. That's what it's getting closer and closer, but never exceeds there. And again, we can see the other thing we can draw is where that point of inflection is. Looks like about right there on our graph. But the key is to label it over here. Remember, this is always half the carrying capacity, so half of 400 is 200. So now we have it all set. So we can see if P of 0 is 30, what's the limit as T approaches infinity of P of T? So as time goes up to infinity, you can see graphically the limit is getting closer and closer to the carrying capacity of 400. So that means the population of whatever it is not going to exceed 400. And then it says, for part B, for what value of P is the population growing the fastest? What value of P, I should say, is the population growing the fastest? Remember, that happens right at our point of inflection here. So that's when P equals 200. Half the carrying capacity. And for what intervals is the second derivative d squared p dt squared greater than 0? Well, if the second derivative is greater than 0, that's just another way of saying it's concave up. Shaped like a cup, so you can see this is the part that's concave up. Now, normally we think about intervals as like x intervals, or in this case t intervals. But on these, you're not going to be able to tell that, but you will be able to tell on the other axis, like the y-axis. That's why it says for what intervals of p. So notice it's concave up when p is between our initial value and half the carrying capacity right there. So you can write it as a compound inequality, 30 less than p less than 200. And then it says, again, for what interval or intervals of p is the second derivative less than 0? Well, that's another way of saying when the second derivative is less than 0, that it's concave down. Shaped like a frown, so that's this part. And that part where it's concave down happens when the population is between 200 and 400. So we can write 200 less than p is less than 400. All right, let's take a look at another example now. So this one, a little different again. Again, it says the population modeled by the function p satisfies. Again, it tells you it's logistic right here. So that's how you know. And this time it's not even in a factored form at all. So that's what we have to do. And remember, we have to get that p isolated on this term here. So let's see what we can factor out of this one. So in order to get it isolated, we look right here. We have to factor out this coefficient, 0.001. And since it's p squared, you also need to factor out a p there. And then let's see what's left. Well, we factored out the p, so that's not left here. We just had 0.3 there. So again, to figure that out, you can think, well, we had 0.3, 0.3, and we factored out 0.001. Okay? So that's like dividing by 0.001 when you factor it out. And this is might be a little easier to think about if you get rid of the decimals. Notice if you want to get rid of the decimals here, to move it 1, 2, 3 places, you multiply by 1,000 and then it's 1. And when you multiply this one by 1,000, it's 1 place, 2, 3. So it's really 300 over 1, so you're left with 300 there. minus, now we just factor out everything except for one of the p's. So now we've got it in the standard logistic form, where k is the 0.001, and now we can see our carrying capacity is right here. Again, you can always double check. If you distribute this out here, 300 times 0.001, that moved the decimal 3 places, 1, 2, 3. You can see you get 0.3 back. All right, so again, before we answer any of these questions, let's go ahead and sketch the graph. So that's what I recommend you do on each of these problems. Sketch the graph of the particular problem, not only to help you solve these problems, but to really ingrain in your memory how to go about solving these and what the graph looks like and the different important features of it. So here it says P of 0 is 12. So that's our initial population is 12 here. And the carrying capacity is 300. Right there. So that's where we'll draw our horizontal asymptote. Might be easier to draw those first and then to sketch the graph of what it looks like. It starts out concave up until some point where it switches to concave down. It gets closer and closer to the asymptote, but never quite touches it. And then the point of inflection right there, you don't have to put it exactly where it is, just try to guess where it looks like it's switching from concave up to concave down. The key again is to label where that happens. Remember, it's half the carrying capacity, so half of 300 would be 150. Again, this is P of t, the population, and this is the time t. So now we have our particular logistic graph set up. Let's go ahead and answer the questions. Again, all these, the P of 0, the initial population is 12. What's the limit as time approaches infinity? So now you look at the graph here, you can see that as time goes to infinity here, the graph gets closer and closer to the carrying capacity, so it's 300. And for what values of P is the population growing the fastest? Again, that happens right at the inflection point there, so when P equals 150. Okay, and for what intervals of P is the graph of P concave up? You can see that's right here, concave up, shaped like a cup, when P is between 12 and 150. And for what intervals is the graph of P is the graph of P concave down? You can see that's right here, concave down, shaped like a pound, 150 to 130. Sorry, 150 to 300, I mean. And finally, for what value P does the graph of P have an inflection point? That happens at the same place where it's growing the fastest, when P equals 150. That's when it's half the carrying capacity is when it switches from concave up to concave down. All right, let's take a look at one that's already, just worded a little differently, already in the right form. Notice this y here, using instead of P, is already isolated there. So, you can already see right here, this is the carrying capacity. So we can sketch a little graph here. We don't have quite as much information here, but enough to answer the question. So the carrying capacity again would go right here on our graph. 800. And that's where we'll have a horizontal asymptote. The thing that's missing here is notice we're not told an initial population. Okay? So we don't know what it is. Something positive, but we don't know for sure what. Okay? And then you can sketch the graph Starts off concave up, and at some point switches to concave down like that. And it says, what are all the values of y? So in this case, instead of p, this is y. This is still time. Okay. But again, y still represents the population, even though they use a different variable here. And it says, what are the values at which the population is increasing? Well, notice the whole graph, the population is increasing. The key is at a decreasing rate. So that means the slope is decreasing, which means the second derivative would have to be negative. So that's really a decreasing rate. It's another way of saying the graph is concave down. You can see it's concave down right here, increasing at a decreasing rate. And notice this would be half the carrying capacity again, where we have that point of inflection would be 400. So where it's increasing at a decreasing rate, it would be this interval. Increasing concave down, you can see the rate or slope is decreasing when it's concave down. So that would be from 400 to 800. And likewise, when it says, what are all the values y at which the population is increasing? Again, the whole graph is increasing. But at an increasing rate, increasing rate is when the slope is increasing, so the second derivative, the derivative of the derivative has to be positive. The second derivative is positive, that means it's concave up. So increasing rate is another way of saying concave up. You can see increasing at an increasing rate, it's getting steeper as it increases. The slope is increasing, so that would be from this initial population to 400. However, we don't know what that initial population is, so all we can say about it is we know for sure it can't be negative or 0, so you'd have to say it occurs between 0 and 400. Normally we would put the initial population here for 0, but we don't know what that is, so the safest bet we can say is, well, it's definitely between 0 and 400, we just don't know what that initial population is. If you just leave off the 0, the only problem with that is then you're leaving the possibility that, if you just say y is less than 400, the possibility that you could have negative y values would work, but we know that's not the case. The population being negative. All right, let's take a look at a few multiple choice ones now. So it says the number of antibodies in a person's bloodstream at time t is increasing according to a logistic differential equation. Which of the following could be the differential equation? So only one of these 6 is logistic. Okay? So here's what you're looking for here. To be in the general, you're looking for the general form here, where this variable occurs twice, here and here. K and C are constants, it's a minus sign there, and you see that variable that's on the top twice, both factored out here or here. Or if it's not factored, you have to factor it yourself. But most of the time on these problems, they'll already be pre-factored for you. So let's take a look at our choices here. So the first ones, notice that we can cancel out here. In this case, instead of p, we've got y, so we should see the y twice here. Here you just see t, so that's definitely not it. Same thing, this one, it's just got a t in it, that's not it. This has t twice, not y, so that's not it. So these are the ones that have y. Notice this one only has the y once, same thing here. This is the only one where it fits the form of the y you see right here, and right here with a minus sign, so this is the only one that's logistic choice to have in this case. E is missing the y out here, and you can see D doesn't have factored form, doesn't have even 2 terms of minus sign or anything, so that can't be a D. Okay, so just recognizing that general form. All right, let's take a look at one that's a little more complicated here. So we've got 8 choices here, and it says P of t is the size of a population at time. To determine whether each of the following differential equations describes linear growth, quadratic growth, cubic growth, logistic growth, or none of the aforementioned types of growth in the size of the population. Okay? So let's start with, we've already talked about logistic growth. Let's start by what linear growth means. Well, linear is a straight line, right? So notice these are all dp dt. So the simplest linear equation you can have is just 1t. instead of just like 1x here. Okay. So let's do linear here first. This would be what linear looks like. So then, sorry, not. I accidentally wrote d p dt, the derivative already. Sorry about that. I meant to put p equals 2. That would be linear, right? And then take the derivative and see what happens. So dp dt when it's linear is just going to be, in this case, 1, right? In other words, a constant. So if you look at all these choices, the only one that has a derivative that's a constant is a. So that's the one that's linear. As you can see, this one would have been 300t, and the derivative is 300. So there's a linear one. Now, quadratic is like a parabola. Quadratic, we'd start off with p equals, the simplest case there would be something like t squared. So then the derivative, something quadratic, would be in this form. 2t, the derivative itself would look linear. Some constant times the variable t. And you can see that one, 300 times t. That fits something that would be quadratic. Okay. So in this case, that would have been like 150t squared, and the derivative is 300t. And finally, before we do logistic, cubic would be something to the third power. So like p equals t cubed. So cubic growth, the derivative, would look like this, dp dt. So the case here would be 3t squared. So the derivative would look quadratic of something that's cubic, something t squared, a constant t squared. So you can see that fits choice C. So that's the one that's cubic. Okay. Notice, then we're just looking for one that's logistic, where the p has to occur in the derivative instead of t, and has to occur twice. You can see that happens on both g and h. They both have p occurring twice in this form. But notice on g, it's a plus sign, not a minus. So that's why h is the logistic growth one. And notice none of these other ones fit logistic growth. This one's missing a p right here. This one only has one term, same thing with this one. So all the other ones, it says or none, would be none. Those don't fit any of those forms. Linear, quadratic, cubic, or logistic. All right. And let's go one more. It says let a of t be a positive constant. Which of the following is a logistic differential equation? So again, they use different letters here to see if you really understand it. So notice instead of y or p, we've got w there. So that w has to occur twice in the derivatives, so it doesn't occur at all on this one. It occurs only once here. This time t occurs twice, not w, so it's not that. Here w occurs twice, and this is a constant 1. That's a constant, so that fits logistic growth right there. And this one almost does, but again, it doesn't because of the plus sign there instead of a minus. So it would be choice D. And that concludes the notes for AP Calculus on the topic of logistic growth.